our founder, Michel Laberge, when he created this company, he was focused on not creating a fusion company, but creating a company that produced electricity from fusion. So that fundamental approach of how do you take this wonderful, science of fusion and turn it into a basic commodity that everyone's going to need, right? That's the approach. And so that's kind of the practical approach of magnetized target fusion in being able to take this forward and getting it into a commercial space for power plants in the future.
Welcome to Evolved Radio, where we explore the evolution of business and technology. I'm your host, Todd Kane. Did you know Cisco helps managed service providers directly? Know about the Cisco Partner Program? Focused on helping partners combine managed service expertise and service creation with innovative Cisco technology and proven go-to-market resources. There's a program option for you. With provider pricing, MDF, and marketing resources coupled with Cisco's leading technologies including Meraki, Duo, and Umbrella. Learn more with the link in the show notes. Today is a bit of a special episode of the Evolved Radio podcast, taking a break from the typical MSP content, as I sometimes do, to explore a topic that's cool, nerdy, and interesting to me as well. Today I'm chatting with Jay Brister, Chief Business Development Officer with General Fusion. General Fusion is a Canadian company and one of the leaders in the race to develop commercial fusion energy. Fusion technology has been around for about 70 years, but has historically remained elusive. Recently, things have changed. Funding of private companies have been rushing into the space as technical advancements are being made regularly. Today, I chat with Jay about the state of the industry and why General Fusion's approach holds so much promise to bring the world a clean and safe source of power to bring us into the future of energy production. If you enjoy the show, please consider leaving a rating and review in your favorite podcast app. It really helps to spread awareness and bring more listeners to the show so we can share the message with more of the community. Now, on with the show. Jay, welcome to the Evolved Radio podcast.
Glad to be here. Look forward to a conversation today.
Awesome. This is exciting for me. I've long had an interest in nuclear energy and sort of the promise that it has for the future. And fusion, I think, has always been a long-held promise, tons of potential, and truly a revolutionary technology. This year in particular has been a pretty banner year for fusion as a technology and the commercial hope for it. So far, in 2021, there was over $5 billion in funding for fusion projects. I think there's about 35 commercial projects around the world that are competing for kind of taking the trophy on this one. And I think that leads to the excitement in the air really being kind of palpable. And it does feel like this time is different. The perpetual joke in fusion is that for 50 years, it's been 10 or 20 years away. And maybe if to start things off, if you could bring us up to speed on just the technical progression of the technology and sort of the state of the industry with sort of those things in mind.
Yeah, no, I'd be glad to. And my common response to that cliche is fusion is now. And I'd like just, be able to support. So, why do I say fusion is now? You mentioned a banner year last year. So the industry itself is really building on, as you mentioned, 70 years of kind of standing on the shoulders of giants, if you will, who've been advancing plasma physics and the science around fusion. But I think there are three critical elements that substantiate why I can say fusion is now. I think first is just the advancements in plasma physics. So I think we know more today about the science of plasma physics. We're confirming plasma theory. We've got some of the best simulation codes and analytics that we've ever had. So the science of this is advancing, and we're really beginning to get a salient understanding of the science side of things. And there's global efforts that the whole industry is taking advantage of down this path. Second is what I'll call enabling technologies. So from a advanced manufacturing perspective, from high-speed computing to high-speed digital controls, we can do things today we couldn't do 2 or 3 years ago, right? The ability to do and deliver coupled with the science is underpinned with the third element of that, which is an astronomical change in funding that's coming into the sector. So when you put all of those together, it means, the science is there, the delivery capability is there. And for companies like us, it's the real ability to go out and hire the right kind of intellectual capital to come in and advance your technology, and funding allows you to do all of that. So it just puts the industry in and of itself in a very unique position. And so, ballparkish 36 of these private, ventures that are out there pursuing this. There's half a dozen that are in a I'll call late stage VC status, as General Fusion is. And we think we're on the fastest and most practical approach to deliver a fusion power plant. But I think that's kind of a snapshot at a high level of, why I'll say fusion is now and kind of what's really driving this interest. And it's, I guess the way I put it, Todd, it's getting to the point where fusion is much more tangible than it ever has been. So projects are starting, big projects are starting. The awareness of where this technology sits, the ability of this technology to fit into a clean energy portfolio in a visible, tangible timeline. All those things are coming to fruition today.
So I feel like it's really coming out of that research stage, right? I've heard your CEO, Chris Mowry, talking about how space is a good comparison here, that for decades, space was just not commercially viable and dominated by governments. And I feel like historically, all the research and applications, just the general expense of trying to research this technology didn't make a ton of sense from a commercial application standpoint. And now that has really flipped in a very similar way in the space race, that fusion is now getting this level of investment because people see the advancement as so far down the line that commercial application is really not that far away. Despite the promises of before, as I said, it does feel different this time, right?
No, that's right. That's right.
Just a quick sort of technical side note. You're talking about sort of the containment of plasma. And as I said, I know enough to be dangerous here, but I do maybe want to understand this, that what is the difficulty of sort of the containment of plasma? Has this been a limitation of like collapsing the plasma in order to generate a fusion reaction because you have to get it in a perfect shape in order to collapse properly? And if there's even sort of micro movements, then it just doesn't work? Is that the issue there?
Well, so for us, and maybe quickly, just a snapshot on our technology, right? So our approach to fusion is called a magnetized target fusion. And if you will, I think it's, on one end of the fusion development spectrum is magnetic confinement, which is the tokamak approach. The other end of that spectrum would be laser-based fusion or inertial confinement. And we're kind of in between the two of those. So it's kind of a, we don't have superconducting magnets and we don't have lasers where we're using, electromagnets and electromechanical forces to create conditions for fusion. So for us, there's a fusion vessel. Inside that fusion vessel is a spinning vortex of liquid metal. And what we do is we have an array of drivers around our fusion vessel, and we control a collapse of that liquid metal that's spinning inside our fusion vessel. And as we collapse this liquid metal inside our fusion vessel, we collapse it in the form of a sphere. And right before that collapses, we inject hydrogen plasma in the form of a ring inside that fusion vessel. And it's the actual physical compression of that liquid metal vortex onto the plasma that creates fusion conditions, 150 million degrees C inside the vessel. When that happens, it's a hydrogen plasma. These isotopes of hydrogen fuse. High energy neutrons come out of that and helium. And it's that high energy neutron that for us is going to heat up that liquid metal. And that liquid metal is a heat transfer mechanism to convert water to steam in a metal to water heat exchanger and drive a conventional power plant. So for us, as we've approached magnetized target fusion, we've been developing these constituent components, so plasma injector, working on our compression system and the control systems independently. We're going to put all that together in our fusion demonstration plant over in the UK. So kind of going back to your question now, this requirement to be able to actually collapse this spinning liquid metal vortex, it's, you talk about the space race. It's really for us kind of migrating away from the science side of things into kind of engineering and operational challenges to advance the technology at this point. So, we had an announcement this week that, our teams have been able to develop this compression system to be actually able to collapse, a spinning liquid vortex in a very controlled manner, in a very even manner, in the matter of milliseconds, right? So that activity is a big de-risking activity for us as we continue to advance our technology and move things forward. So it's a great engineering solution to a problem that people have been trying to solve for a long time. And just a great team of folks in Burnaby that are working on this.
That's amazing. So it does bring up another side note that I wanted to ask later as well. But since you mentioned it, I understand like one of the challenges of this is the materials required to contain and manage such a sheer amount of energy and heat is part of one of the challenges of this technology. But perhaps you could help us understand, how exactly do you contain something that's 120, 150 million degrees Celsius without it just liquefying everything within a block radius?
Yeah. I think here, once again, that's one of the unique advantages that magnetized target fusion delivers as far as a fusion technology. Again, I'll go back to you've got a fusion vessel, and then you've got a meter and a half of liquid metal that's spinning around in there. So when you compress this liquid metal and fusion occurs, I mean, it happens, very, very quickly. And these high energy, so there's a very instantaneous occurrence of fusion. And for us, the inherent characteristics of having this liquid metal inside the vessel, number one, it acts as a shielding mechanism for the physical vessel itself. So there's longer term benefits where you're protecting that kind of critical piece of the infrastructure. Whereas in a tokamak design, I mean, you have this thing called the first wall problem, right? And it's exactly what you're describing. It's just the degrading effects of putting fusion conditions in contact with the vessel itself. So they're still working very hard on that, and using things like lithium to help solve that kind of problem. But I think with our approach, it's having that, kind of the twofold benefit of having that as a shield. But number two, it's actually that heat transfer mechanism. So our founder, Michel Laberge, when he created this company, he was focused on not creating a fusion company, but creating a company that produced electricity from fusion. So that fundamental approach of how do you take this wonderful, science of fusion and turn it into a basic commodity that everyone's going to need, right? That's the approach. And so that's kind of the practical approach of magnetized target fusion in being able to take this forward and getting it into a commercial space for power plants in the future.
So if I understand that correctly, it's essentially like the magnetized conditions are suspending the products inside and at that heat. Mm-hmm. So it's not really touching anything. So therefore you can kind of sustain that level of energy. Is that right?
Yep. Yeah, sure.
Okay, cool. You also mentioned something that I think is incredibly important, and I think a distinction between some of these different projects that are operating, and in particular for General Fusion, that there's sort of twofold ideas or targets that people are trying to get to with the technology. Ideally, it would be amazing to have net positive energy, where you're introducing less fuel than the reactor actually produces, and this is sort of the gauntlet or the holy grail of fusion, but not necessarily what some of the projects are targeting near term. And General Fusion is looking for more of a power plant approach, where you're not necessarily looking for net and positive production outputs, but just a better power source that could fuel power grids and commercial applications and other things like that. Can you maybe touch on the differences in those objectives in the technology?
Yeah. So, I mean, I think kind of where the industry sits and our approach to this as well is because of the nature of fusion, we're able to build demonstration facilities. And that's kind of the next big milestone for the industry. And you'll see that occurring as we go through the middle of this decade. And we could talk more about our project later if you'd like to. So it's about, for us, being able to actually, take our constituent components we've been developing there in Burnaby and design our fusion demonstration plant and be able to demonstrate at power plant relevant scale. So this machine that we're building will be about 70% the size of an operating power plant. So it's a 3,000 ton machine we're going to build in an 11,000 square meter building. So it's basically a power plant without a power plant attached to it, right? The power producing pieces of that, right? So, and it's about demonstrating that at a power plant relevant scale, we can actually create the conditions for magnetized target fusion. And by doing them at that particular scale, we can then take that data set and actually create that power plant that is going to achieve all of those goals that you mentioned and also produce electricity. The other big benefit we get by taking this kind of two-step approach, there's some fundamental economics around this as well. So number one, we want to do this in the most cost-effective way that we can to take advantage of the funding that we have to get the most bang for the buck out of that. But also, as we build this facility, it'll give us a good baseline for the economics of what our next evolution of the machine will be. So as we go into producing a power plant, as we do go forward, it's all about the economics of the product that you produce and the ability to do that that's going to be comfortable for a customer's wallet in the long run, right?
Sure.
So we've got to meet those goals as well, or say we're not going to get there.
Right. I've heard sort of your target power plant would be 100 to 200 megawatts. What is the power output expectation of the demonstration facility that you're building?
So it is going to be just a fusion demonstration facility. It will not be power producing. So it's all about demonstrating the technology. So for example, in our operating power plants, that compression system, it will be doing that between 1 and 10 times a second. In our fusion demonstration plant, we'll be doing it 1 to 2 times a day.
I see.
It's about really focusing on, taking all of this new power plant scale equipment and validating the magnetized target fusion approach.
Right. So it works. We can repeat this reliably. So therefore, we can build something in a larger scale, correct?
Yes. Perfect.
And I imagine that there's a sort of a continuum that you follow in this, that the next step would not necessarily be a power plant, but maybe smaller commercial applications like say an industrial facility that would otherwise use dirty sources of power or other sort of applications. You could maybe build a smaller fusion reactor for those industrial applications. Would that be the next step, or what would be sort of the next step after that demonstration facility?
What we're doing is a great question. And, we're on, I'll call it a 5-year path towards commercialization of our technology. So we're just trying to get to the point where the designs of cells and the technology performance has advanced to the point that we're able to take this product to market. So in addition to the efforts that we have around designing and delivering our fusion demonstration plant, we're also developing the design basis for our power plant. That will be going on in parallel with the development of our fusion demonstration plant. So when I look, ahead into what's the application of this particular technology in the marketplace, as you mentioned, electricity is there, but industrial applications are there. Possibly even marine applications are there. So, so it's coming up with that right kind of standardized product that's going to be there to do what it needs to do for a business application for commercial delivery of a technology. But as the technology continues to advance and evolve, especially the benefits of carbon-free fusion power being realized, I think there'll be a much broader kind of diverse application of the technology as it does go forward. With the main drivers, I think, in the marketplace today, that the biggest kind of collective global benefits are getting fusion introduced into the production of electricity to offset, these carbon sources that are in the market today, which are in North America. It's one of those things where, sometimes it's great to be a consumer of electricity today because it's just so cheap, but underpinning that are some strong carbon-based components that go into that. So we'll have to go through this energy transition and see how all of that is going to work, but getting fusion into that mix to become part of, an integrated resource plan and time that as we go forward with the development of technology. Those are kind of some of the levers that we're having to look at as we look at going forward to commercialize the technology. Yeah,
the green application, the rebuilding of the power grid, those are absolutely some things I want to hit on. So we'll get to that next. One thing I did want to sort of hit on as far as sort of the nearer term commercial applications, one that I find is really exciting and really promising is water desalination. And I think this is not something that occurs to people, but the access to clean water, potable water, and water that is drinkable, I think, especially going forward, is going to become an incredibly difficult thing to manage for people in very particular areas around the world. And the difficulty with water desalination is that it's totally possible, but it is incredibly energy intensive and not really practical.
Right.
So, having a green source of energy, especially kind of a smaller scale power source to do these types of things, I think would be really advantageous for those types of applications. Are those some of the things that you guys are considering as commercial options in the future?
Well, I mean, maybe I'll just give you a frame of reference here. I had the opportunity for work for several years in the United Arab Emirates. So desalination is core to them being able to produce water, for their nation. And it's just interesting as they develop power projects, they develop water and power projects together. So you're building a power plant, but also coupled to that is a desalination facility. So what we're doing is we're creating a carbon-free energy source. So that application can be very, very diverse in how it's delivered. So the other tangential, application could also be hydrogen production, right? So again, if you're going to do this with electrolysis, you need a clean source of electricity to get green hydrogen out of that. So, on one side of the equation is how is the energy produced that's going to produce this secondary product. And if you can do that in a carbon-free manner, there's a lot of different applications for the technology as it goes forward.
Right. Okay, great. So yeah, I didn't realize that they built the power source and the desalination together. That makes an incredible amount of sense and sort of further validates that as an application. So that's interesting. So the other one that you said I wanted to come back to is sort of the refitting of the green infrastructure from a global power grid. And I watched a TED Talk or a podcast or something recently that I listened to that really keyed me into something that I hadn't considered beforehand. I think I knew this, but hearing someone talk about it really had it resonate with me in that one of the major challenges to creating a green energy grid is most of the sources for solar and wind in particular are in areas that are very, very far away from where that energy would be consumed. And that's a huge issue around how you actually rebuild a power grid so that people that need the energy are able to access that energy in an efficient manner when it's generated so far away. So I think the transmission and the storage of that energy is going to be a critical component of rebuilding that grid. But I also see fusion as a really powerful source to supplement those high density, high draw areas where you do need a core source of energy. You can't necessarily rely on wind, but you also want to move away from natural gas and coal and other dirty sources. So I think it's really important that you guys are focusing on the power plant generation as a component for the refitting of the grid. Can you maybe expand on sort of your thoughts and the company's thoughts on how you fit into the rebuilding of the grid in the future?
Yeah, and I mean, you hit the nail on the head. So it's quite an incredible challenge to find those parts of the world where wind and solar, there's an ideal application, but it's the remoteness of that is usually the downside and having to create the infrastructures to be able to support that. When you integrate fusion into kind of a going forward carbon-free energy portfolio and you run some economic models around that to try and, you optimize what is going to be built kind of based on the economics and eventually kind of that end price to the customer. How do I do this such that economically I'm going to pass those tests that I need to get to the point where I'm going to be selected and dispatched as a fusion power plant, right? When you introduce our plant into the mix, I mean, our economics are, right now we're looking at about $50 to $65 a megawatt hour. So, something that's very competitive with coal, for example, in the market today. When, we've done some analysis around that, and I see fusion as just, there's a hand in glove fit with renewables, with what's going on, because renewables, the cost for that continues to come down. And I saw, I think, a report, just news bite came in this morning that was forecasting that, for example, in the United States, that renewables were going to be the largest build out of any energy source in the United States during 2022. So, I mean, the amount of renewables is going to continue to increase. But when you put fusion into that mix, you get a baseload dispatchable source that can complement the intermittent nature of renewables. The other thing is you can put it right next to the load. The safety requirements for this particular technology are going to be very, very different than fission-based requirements, right? So it's a very different technology from a radiological risk management perspective. So being able to, number one, put these things close to the load and then allow them to complement combating the effects of that duck curve as the wind quits blowing and the sun goes down. What are you going to have to turn on to make up for that, to maintain a steady output? Fusion can fit into that mix and actually just kind of underpin it. So when you look at how do I get to a greener grid application, I think the renewables will go where they go. I think the other thing to look at too is when you put fusion into that mix, it actually is going to offset some of the renewables you would have to build to get to that, to get to the demand side of things. So, it creates, more of an integrated energy portfolio to be able to be a truly green, decarbonized portfolio. But the other kind of, ancillary benefit that is there are just some very, very significant land use savings that come into play there as well, right? I think one last maybe thought on this one is it's going to be interesting to see how renewables continue to grow, because I think, I guess the way I look at it, I think a lot of the renewable projects, the easy ones have been done.
That's right.
So as the land use requirements there's a little bit more encroachment. I think we're seeing, both in North America as well in Europe, it getting to the point where there's actually moratoriums being set on any additional wind. So it's going offshore, and that will have its own set of challenges to deliver. But, those will be overcome, and we'll have some big offshore wind farms, but we're going to have to complement that with carbon-free fusion on the mainland.
Yeah, right on. That does lend itself to sort of where these things are placed. And you mentioned that fusion is categorically much, much safer than a fission reaction. The safety profile is much, much different. But, to people that don't necessarily understand nuclear physics and are not sort of up on the science of that, the people tend to still be very wary of nuclear energy. And I think that's based on technology that was built in the 40s and 50s in a lot of cases. And it's not even necessarily applicable to fourth generation nuclear technology. It's certainly not applicable to fusion, but there's still that psychological profile or an issue that you have to overcome with people. I imagine you guys must have faced this. And what are your thoughts around educating people around the safety of fusion, especially as you're trying to build a demonstration facility? I imagine you ran into some resistance of people saying, no, you can't build a nuclear power plant in my neighborhood, right?
Yeah. Well, first we did a global search for about 3 years to figure out, what's the best place to put our fusion demonstration plant. And the United Kingdom was gracious enough to host us at the UK Atomic Energy Authority site there at Culham. So a very unique set of conditions there. There are already fusion machines there. The Joint European Torus is there. So, it was a very open and easy pathway to be able to deliver that machine, as we do go forward and deliver all the governance and things we needed were there. So that made that kind of a hand in glove fit. I think as we go forward, I think there's a parallel here that we can look at to kind of maybe help maybe gauge where the public sits on this, and as a tool to help the public further understand kind of this new technology that's being developed. And that is how is this new technology going to be regulated? So there really are no regulations for fusion power plants yet, right? But if you go back and kind of look at the set of regulations that are in place, when you look at the kind of radiological risk that is needed to be managed, it's already written in the regulations. It's just that fusion is not there, right? So as an example, if you look at what's happening in the United Kingdom, they're looking at how do I get fusion technology into my country? So they looked at the regulations that were set forth for fusion, for fission, for other technologies. And they've come up with a path forward there where they basically said, we've looked at fusion. We think the risks associated with oil and gas are higher than they are with fusion. So we're going to use our existing health and safety executive regulations and our existing environmental regulations with a couple of clarifiers on that. And that's going to be our fundamental basis to regulate fusion within the United Kingdom. So that's just gone out for a period of public comment throughout last year that closed, and they'll be taking that forward. So it's actually going to be regulated outside of their existing nuclear regulator in the United Kingdom. So, Canada is looking at that as well. The CNSC has done their initial look at fusion and how to develop fusion regulation. So that will be forthcoming as well. And then south of the border, the USNRC is having their series of public meetings on this. It's throughout the whole last year. They've been doing that. So they're beginning to move forward and come up with a path forward. And again, if a country's got a nuclear medicine program, if they're doing academic research with particle accelerators, there are regulations that are there to kind of govern that already. So equating it to the kind of what's there. And for us, we're a carbon-free, clean technology. That's what we are. So it's just a little bit of differentiation in there between where we are, what's underneath it. I mean, it's still science that's going on underneath all of this, and being able to, as we do go forward, educate everyone with where we are and what's going on to have a better understanding of the technology is essential.
I imagine like the different groups that are targeting some of these projects and doing the advancement of this science. I assume you guys are chatting with each other about some of these challenges. Have you ever considered like a consortium that could help kind of publicly educate people about why fusion is different to sort of reduce that resistance that you're going to face at some point in the future?
A fabulous question. And actually, to that end, in the United States, there's been a group put together called the Fusion Industry Association. So it's really the collective, almost, global fusion industry and supporting companies that are interested in fusion or the eventual delivery of fusion. And it's exactly those principles that the fusion industry is focusing on. It's focusing on getting the right type of regulations put in place that are the appropriate level of risk to the technology. And number two, what are the FAQs on fusion that we need to answer, right? So let's just get that out there and get it set. So it's a kind of here's our sheet of music, right? So it doesn't matter if you're in England, in Sweden, or in Vancouver, you're going to be singing from that same sheet of music.
Right. Perfect. And maybe just quickly, like to digress a bit on the nerdiness of the science as well, is again, like I know enough about nuclear energy to be dangerous here, but I don't actually understand. I understand how they're different. Obviously, fission being the splitting of an atom to produce energy, fusion being to smash things together and fuse them together. Why is it that fission creates such a sort of a dirty profile of waste? Is it just the way that the coolant works, or what is it that fusion does not have the same byproducts as fission does?
Yes, let's just I've got a background in fission as well. So when you look at at a very simple level, fission is really taking one of the heaviest elements and you're splitting that element. And fission as a reaction is relatively easy to start,
right?
But it's hard to stop.
Mm.
So it's hard stuff. So there are layers of regulations that go around that govern how that fission reactions has to be managed, and then it's just the nature of the technology, the nature of the fuel, and the nature of the byproducts from that. It has its own inherent set of characteristics. So there's a whole set of regulations that are put in place to govern and manage all of that. On the fusion side of things, we're taking isotopes of hydrogen and fusing those together, and we're creating energy and helium. The byproduct there will be tritium, which can be managed, but it's in such small quantities. So the way I would look at it, it's, again, it kind of goes back to that nuclear medicine analogy. In fusion, it's more so setting up regulations that are focused on kind of the health and safety of the worker as opposed to the broader health and safety of the public. So it's just a magnitude. I mean, the regulations are there. They're risk-based. And so they're very appropriate for what has to be applied. And for us, as we do go forward, it's just kind of wrapping things with the regulatory cover that need to be there to, number one, provide that level of protection that the public's looking for.
Okay, so if I understand this correctly, it's the nature of the fuel being used in fission reactions and the fact that you can get it started, but it may be a hell of a lot of work to slow it down, which creates kind of a risk profile. And I guess the inverse is true for fusion, is that the fuel sources, what you're using to manage the reaction, is fairly benign in most cases, and it's actually more difficult to sustain.
So it's kind of just the opposite. It's
right.
Very, very hard to start, but be very easy to stop. Right. So
right.
That's those accident scenarios just aren't there.
Right. Okay. I guess looking to sort of wrap up here, one of the other applications, more on the long term, but I imagine you guys may have thought about this, but space applications, I think in the future would be huge for this as well, is that certainly the size of the reactor being really beneficial. the low necessity for huge fuel sources. One of the most difficult parts of getting to space is you have to carry all the fuel with you, which adds an incredible amount of weight. And then not being able to sort of sustain that and keep enough energy on board a vehicle in order to now move around in space. And I think fusion would be revolutionary in that. And, anyone who's a sci-fi fan will certainly recognize like any spaceship kind of worth being in a futuristic sci-fi scenario is largely running on fusion. So have you guys sort of thought about that or had any type of discussion with people on potentially testing some of these technologies in space?
Yeah. I'll go back to the Fusion Industry Association again. There's actually a space subset of fusion that's very active. So, the things you just mentioned, the development of technology, be able to support applications in space. There's people that's their day job every day right now. So they're working on that, trying to develop that.
Right on.
I mean, different size and scale of a power plant, right? So it's a different application, but there are governments putting out procurements looking for how do we do this kind of thing. So yeah, it's something that is active globally.
And maybe just to circle back on something else you mentioned, the fact that you guys can sort of as a byproduct produce hydrogen, and that would potentially be used as a storage vehicle. So you're producing the energy as well as kind of the necessities for a battery for that energy as well. Is that right?
Well, I mean, yeah, it goes back to the economics of, what's the ultimate cost of electricity going to be that's going to drive the electrolysis, which is going to drive the cost of what that hydrogen product is going to be. So it's just continuing to kind of watch how the hydrogen market is going to continue to evolve. And will there be, I think there's some newer technologies that are not based on electrolysis where process heat can be used to develop the hydrogen. But if you can do that in a carbon-free manner as well, that's another application. But again, it's one of those things as the energy transition occurs. I think there are going to be lots of pathways that get explored to see how do we create this right portfolio of energy technologies that do get us to the point where we are carbon-free. And, fusion is going to be part of that mix. And I think as we go forward, it's determining, the best and then the diversity of applications the technology can fit into kind of to meet the global needs to get us where we need to get to.
Okay. And also recognizing that net energy production is not necessarily a near-term goal. Like I said, it'd be the ultimate holy grail. But is that something that the industry is looking for in kind of the next 20 to 30 years? Like a commercialization of using this as a viable production of energy for power plants and power sources. But then, true net energy output is, I have to imagine, is a longer term goal, right?
Well, it's globally, there's a lot of research and development going on for fusion science, right? So Italy in the south of France, got the joint European Taurus there in the UK. And then, there's activity in China. There's activity in South Korea. There's activity in Japan. So there is a tremendous amount of effort to achieve this milestone. And I don't think that it's decades away. I mean, I think it's something that's going to happen. It's going to happen probably again sooner than we think with the amount of effort that's going into some of these really big projects and some of the kind of this bow wave of announcements that's been coming out as technology develops, movements do go forward. And again, that's to the collective benefit of the whole fusion sector, because we're all getting to take advantage of what they're learning, what's being delivered, and how you can take that and put it in an application that we can get commercialized. So maybe to wrap up, it's really, the government work that's been going on has just been phenomenal. The advancements in science have been phenomenal. But it goes back to that little SpaceX analogy you mentioned a little bit earlier. So it's really, you had decades and decades and decades of NASA doing what they did, and the science there and the technology was there. But then you needed to, instead of move at the speed of government, you needed to move at the speed of business. So that transition, I think, is where we are today with fusion. So it's migrating and integrating those types of applications together to move things forward.
Right on. Very, very exciting times. I really appreciate you coming on and bringing us up to speed, Jay. This is all awesome stuff. I guess finally, you guys are actually looking at this as a commercial application within 10 years, like within the decade, right?
Yes. Our goal is to get our fusion demonstration plant. We're going to put the shovel in the ground for that a little bit later this year. And then that machine will go operational in 2025. and we'll further our power plant design throughout the course of this decade with a goal of getting a shovel in the ground by the end of this decade and commercial operation early in the 2030s.
Amazing.
So that's our development timeline. Yes.
All very exciting stuff. I think you guys are certainly one of the leaders in this industry. I'm sure you would agree, and really exciting, especially cool that you guys are local as well. I definitely like to spotlight some of the amazing research and development and entrepreneurship that's going on in BC as well, being kind of where I'm from. So really neat that you guys are local as well as one of the world leaders in the race for fusion.
No, very, very excited to be here. We've just got such a great talent of young scientists and engineers that are part of our company as well. And, we're growing and expanding. So we're about to move out of Burnaby into a new expanded headquarters down at YBR. So, the growth continues, and we're almost doubling in size, tripling in size. So, this going forward momentum for us, and be able to, but I guess the brain trust is going to be in Vancouver, right? That's where we are, and that's where we're going to grow this from, and really and truly for the benefit of the world.
Awesome. Appreciate it, Jay. Thank you.
Yeah, you bet, Todd.